A research details a groundbreaking scientific advancement spearheaded by chemist Yue Gu of Rutgers University, which proposes a novel, chemistry-driven solution to the persistent global crisis of plastic pollution. Inspired by the elegant functionality and disposability of natural biological polymers, Gu and his research team have developed a method to engineer synthetic plastics with a built-in, programmable expiration date. This innovation, published in the prestigious journal Nature Chemistry, aims to reconcile the indispensable utility of plastics with their devastating environmental persistence by fundamentally redesigning their molecular architecture. The narrative begins with a poignant, personal catalyst for the research. A hike through Bear Mountain State Park in New York, where Gu was confronted with the jarring sight of plastic bottles littering a natural landscape. This encounter starkly highlighted the central paradox that his work seeks to address. Both natural materials and modern plastics are composed of polymers, long, chain-like molecules made of repeating units. Nature relies heavily on polymers like DNA, RNA, proteins, and cellulose, yet these materials efficiently break down and re-enter ecological cycles. In contrast, synthetic plastics, designed for durability, persist in the environment for decades or centuries, leading to catastrophic accumulation. Standing in the woods, Gu had a key realization. The difference has to lie in chemistry. He understood that biological polymers are not just structurally sophisticated, they contain subtle, built-in chemical features that act as a built-in exit strategy. These features ensure that the strong bonds holding the polymer together can be reliably broken at the appropriate time after the polymer has served its biological function. Gu posed a transformative question. What if this structural trick from nature could be copied and applied to human-made plastics? Could we design plastics that retain their strength during use, but are pre-programmed to disintegrate under everyday conditions, without requiring industrial composting, high heat, or corrosive chemicals? This question formed the foundation of a significant breakthrough. The research team set out to tackle one of the most formidable challenges of modern materials science, creating plastics that degrade naturally under ambient conditions without special treatment. Their goal was not merely to make a biodegradable plastic, a concept that often requires specific managed environments to function, but to invent a new chemical strategy that embeds degradability directly into the material's DNA, so to speak. To understand the innovation, the research explains the basic chemistry of polymers and bonds. Polymers, whether natural or synthetic, are like strings of beads, where each bead is a molecular building block, like nucleotides in DNA or monomers in plastic. These beads are held together by chemical bonds, which act as molecular glue. The exceptional durability of conventional plastics stems from the formidable strength of these bonds, particularly the carbon-carbon bonds that form the backbone of most common polymers. This same strength, however, renders them nearly impervious to natural degradation processes once discarded. Gu's research focused on ingeniously redesigning these bonds. Instead of relying solely on ultra-strong links, the team designed chemical bonds that are stable during the plastic's useful life, but incorporate strategically positioned weak points. These weak points are not flaws that compromise initial integrity. Rather, they are carefully engineered molecular arrangements that remain dormant until activated. The core discovery is that by installing specific neighboring chemical groups in an exact spatial orientation along the polymer chain, the team can dramatically accelerate the breakdown process. These groups are positioned to interact and facilitate a chemical reaction that severs the polymer backbone, much like a precisely placed perforation on a piece of paper makes it easy to tear along a straight line. Gu uses the analogy of folding paper to create a crease. By effectively pre-folding the plastic structure at the molecular level, the researchers can make it fall apart thousands of times faster than an identical plastic without this design vulnerability. Crucially, until the degradation is triggered, the plastic's overall chemical composition and mechanical properties remain unchanged. It is just as strong, flexible, and useful as a conventional plastic. This addresses a major shortcoming of many existing biodegradable alternatives, which often sacrifice performance for degradability. The most profound implication of this work is that it makes plastic degradation programmable. The research demonstrated that by precisely controlling the orientation, positioning, and density of these built-in weak points, scientists can engineer the same base plastic to break down over a predetermined timeline, whether that is days, months, or years. This level of control allows for the rational design of plastic lifespans to match their real-world applications. For instance, single-use food packaging or disposable medical supplies could be designed to degrade within weeks after use. In contrast, plastics used in automotive parts, construction, or electronics could be engineered to remain intact for decades to ensure safety and performance, yet still contain the latent chemistry to break down eventually, far surpassing the centuries-long timeline of current plastics. Furthermore, the method offers flexibility in how degradation is initiated. The self-destruction mechanism can be designed to start automatically after a certain period exposed to ambient moisture and heat, or it can be triggered on demand by a specific external stimulus. The researchers successfully demonstrated activation using two common triggers: ultraviolet light, akin to sunlight, and metal ions. This means a plastic item could remain stable indoors or in storage, but begin to degrade once exposed to sunlight in a landfill or natural environment, or even be processed in a recycling facility with a specific chemical trigger to aid decomposition. The potential applications of this chemistry extend far beyond mitigating plastic pollution. Gu envisions a future where this principle of programmable molecular stability is applied across multiple fields. One promising avenue is in biomedicine, for creating timed-release drug delivery capsules, or self-erasing medical coatings and implants. A capsule could be engineered to remain intact through the stomach and then disintegrate at a precise location in the intestines, or a post-surgical coating could protect a wound for a set number of days before harmlessly dissolving. This smart, responsive material design could revolutionize areas from pharmaceuticals to electronics. For Gu, the long-term vision is elegantly simple. Plastics should do their job and then disappear. His strategy provides a practical, chemistry-based pathway to redesign these ubiquitous materials so they align with ecological principles. Early laboratory tests are promising, indicating that the liquid byproducts produced when these programmed plastics break down are not toxic. However, Gu emphasizes a strong commitment to responsible development, clearly stating that extensive further testing is imperative to confirm the long-term safety of both the breakdown products and any residual microfragments for living organisms and ecosystems. The research concludes by outlining the ongoing and future direction of Gu's research. His team is actively expanding their work in several critical areas like comprehensive safety assessment. They are meticulously investigating the environmental impact of the small fragments generated during degradation to ensure complete biocompatibility and ecological safety throughout the material's entire life cycle. Industrial scalability. The researchers are exploring how this novel chemical approach can be adapted to modify existing, widely used conventional plastics, like polyethylene or polypropylene, and integrated into standard manufacturing processes. This is crucial for translating laboratory success into commercially viable, large-scale production. Broadening applications. Concurrently, they are testing the method for creating advanced drug delivery systems, proving the versatility of the core chemical concept. While significant technical and commercial hurdles remain, including cost-effective synthesis, performance optimization for specific uses, and seamless integration into global supply chains, Gu is optimistic. He believes that continued scientific development, coupled with collaboration from forward-thinking plastic manufacturers committed to sustainability, can bring this nature-inspired chemistry into everyday products. The story, which began with a moment of reflection in a polluted park, stands as a testament to the power of bio-inspired design, offering a scientifically elegant and potentially transformative tool for addressing one of the most stubborn environmental challenges of our time. The research was a collaborative effort within Rutgers University, with key contributors including Xiaozhen Yin, doctoral student and first author, Associate Professor Lu Wang, doctoral student Rui Zhang, research associate professor N. Sanjeeva Murthy, and former undergraduate Ruihao Zhou.